Good morning, students. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC702C. Topic Magnetrons. Magnetrons are basically oscillators invented by Hull in 1921. These are cross-field tubes in which the applied electric and magnetic fields are perpendicular to each other. Magnetrons can be classified into three categories. First one, split anode magnetron. Second, cyclotron frequency magnetron. The third one is cavity magnetron. Split anode magnetron. This type of magnetron uses a static negative resistance between two anode segments. It operates at frequencies below the microwave region. Cyclotron frequency magnetrons. It operates at frequencies in micro range, but their power output is very small and efficiency is very low. Cavity magnetron. Cavity magnetrons depends on the interaction of electron beam with noisy RF voltage present in the interaction space. 8 cavity cylindrical magnetron. This is the constructional diagram of 8 cavity cylindrical magnetron. It is a diode, usually of cylindrical configuration, with a thick cylindrical cathode at the center, and a coaxial cylindrical block of copper as anode. The space between the anode and cathode is called interaction space. This is the interaction space. One of the cavities is connected to a coaxial loop to extract the output. The applied electric field between anode and the cathode is along radial direction, and the applied magnetic field produced by a permanent magnet is axial. That is, the applied electric field is along the radial direction. The applied magnetic field produced by permanent magnet is along axial direction. These two are perpendicular to each other. That is why magnetrons are called cross-field tubes. Depending on the relative strengths of the electric and magnetic fields, the electrons emitted from the cathode moving towards the anode will traverse through the interaction space. Constructional details in 3D view. Operation of magnetron. Case 1, in the absence of noisy RF field. If the magnetic field is equal to 0, the electron travels straight path from cathode to anode. That is, here the radius of the electron path is given by R equal to mv by Eb. B is the magnetic field. In the absence of noisy RF field, if B is equal to 0, the radius of the electron path is infinity. That is shown by path A. The magnetic field strength increased slightly, it will exert a lateral force bending the path of the electron as shown by path B. The strength of the magnetic field is made sufficiently high. The electron bends more sharply and never reaches the anode as shown by path D. The minimum magnetic field required to prevent the electron beam from reaching the anode is called critical magnetic field, that is shown by path C. Case 2, in the presence of noisy RF field between the cathode and anode, that is in interaction space. Initially, we are assuming that the oscillations are set up in the tube due to noise or switching transients and are sustained by device operation. The electrons A, C and D are seen to be slowed down in the presence of noisy RF field, thus transferring energy to the oscillations during the longer journey from cathode to anode. Now here we are assuming that some noisy RF field is present in the interaction space. The electrons generated by the cathode affected by this particular noisy RF voltage travels in paths A, C, D. Such electrons which participate in transferring energy to the RF field are called favored electrons. These electrons are responsible for bunching and are called favored electrons. Here, the electrons A, C, and D are seen to be slowed down in the presence of RF field, and these electrons form bunching by losing energy. And here, the amount of energy lost in formation of bunching is transferred to the noisy RF field which is present in the uh, interaction space till the oscillations are sustained. The electron B is accelerated by the RF field. Instead of transferring energy to the oscillations, it takes energy from them, resulting in increased velocity and hence bends more sharply, spare a little amount of time in interaction space, and these electrons are called unfavored electrons. The magnitude of the magnetic field doesn't affect the velocity of the electron, it just bends the electron path. The velocity of the electron beam is given by v square is equal to vr square plus v pi square. Here vr is the radial component of electron velocity, v pi is the angular component of electron velocity. The relative phase change of AC electric field across adjacent cavities is given by pi v is equal to 2 pi n by n, where the value of small n is from 0 to plus or minus n by 2. If small n is equal to capital N by 2, pi v is equal to pi, and this is called mode of resonance. If n equal to 0, pi v equal to 0, this is called 0 mode. Thank you. We will meet with the next lecture.